Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I left off last day. Last day I started talking about amortized analysis. So this is kind of one of our first topics for data structures. So last day I gave you just a general idea of why we might care about having a more delicate way of looking at worst case analysis for some of our data structures. So for example, we talked about the scenario. For example, if you were to have a data structure where you perform insertions into an array, there's a real possibility that your data structure, in this case, our underlying one, our array becomes full. We may run into a problem where we need to resize, say, our underlying array, and that might be a very expensive operation. But the point is it doesn't happen very often. And I would like to have some type of analysis to help me delineate from those cases for which those expensive operations happen infrequently, or perhaps to measure costs of operations per the sequence I'm looking at. Because it's not just one operation we will usually be interested in for a data structure. Instead, it's a sequence of operations. For example, in practice, you don't just do one operation on a data structure. Normally, you do a sequence of operations to manipulate the data structure, whether it be doing insertions or you might do some removals. The whole idea here is that we want to have some way of capturing this type of situation, which is quite more realistic than just looking at a single operation in the worst case for a data structure. So the big idea here is that imagine instead of just thinking about one operation, imagine we have a sequence of operations and we're going to look at the worst case running time per operation. So that's what we mean by amortized analysis. So for those that may be big into finance, you might heard this term amortization before. It's over the period. And the whole idea, the intuition behind this is that for some of our data structures, we would like to have it where we have many cheap operations that can occur so that over time, those cheaper operations can help us pay off, say, much larger, more expensive ones. So there's a few different ways you can think about that from an amortized analysis standpoint. But for us, we're going to use essentially this very common method called the aggregate method. It follows directly from this definition that I have up here. So if I give you a sequence of operations, I want to know the worst case running time per operation. A very natural way to calculate this is quite similar to the example I did last day, but I'm going to do this in a far more particular way this time. Imagine I have the total cost of performing n operations. Notice that n here is the number of operations. It isn't the input size here. It's actually the number of operations, so just be very wary about that. So remember, we're dealing with a sequence of operations, and suppose the total cost of all of these operations. So when I mean total cost, I'm talking about if you counted up the number of operations for your sequence. So if I total all of those up over all those operations, I'm telling you that is going to be big O of t of n, or big O of t. So if I want to know the amortized cost or the amortized complexity, all I simply do is I take the total cost over the number of operations I did. And that's how you calculate the amortized complexity using this aggregate method. So are there any questions about this definition before we proceed? Any at all? Because it's going to be very important for this lecture today. Any at all? Or does this seem pretty darn straightforward? Is that I have all my operations, I'm going to sum up the total cost of all of those, and I'm just going to divide it by the number of them I did. Okay, so if there aren't any questions, I want to kind of give us a breakdown or game plan for what we're going to do here. So in amortized analysis, so notice that when we did worst case analysis, we identified a worst case scenario, right? That's what we did. Now, what I would like to do is do something like this, but with a sequence of operations. So what I want to do is I want to identify a sequence of n operations and what the cost of doing each one of these operations would be. And then I want to find some way of summing all those up. So that's the first kind of big piece of this. The other piece is I would like to have a sequence so that I can cause it to have the largest possible cost over any sequence. So the idea is to compute the largest possible cost across any sequence of operations we are interested in. Then we just simply divide that by n. So you might ask, okay, so what does this mean? This means that I'm going to look for what tandemounts to a worst case sequence that's going to cause these operations to be the ones that are the most expensive to happen as frequently as I can. And you might notice that I talked about operations we are interested in. So you don't have to just talk about a single operation. For example, we're going to see an example where I'm going to perform a sequence of insertions. You can actually take combinations of operations. So for example, you can have insertions and removals. And you can take a sequence of those and measure how expensive doing any sequence of insertions and removals for your underlying or of your data structure. So you can do this. So the whole idea here is I'm going to give you a scenario. Now, if I'm just doing this for one operation, there's really only one thing that can happen, right? I just keep doing the operation and we see how expensive each one gets as we fill up the data structure, right? If I have two or more, what'll happen is you'll normally want to look at what the data structure does on an insertion or removal and try to figure out a way to make it so that it consists of both of those types of operations, but try to make it as expensive as possible. But for us today, I'm going to focus primarily on when we only have one operation that's going to happen. Because once you see it once, it really helps. And also I'm going to give you as well a very general scenario that you can easily apply to many, many different kinds of linear data structures that use an array, for example. For example, you should be able to pick up, for example, I keep saying the word example, that's how excited I am. I'm going to, if I were to do this again with, say, a stack or a queue or any other data structure that, say, is implemented with an array-based approach that does something very similar to this, the analysis will be very similar. That's why I want to show you this. It's that you're going to find that this analysis approach we're going to use is going to be fairly general. And I also want to justify something for you. I have a question for you. So when we talked about, so probably you talked maybe about this in 210. Maybe when you talked about stacks and queues or potentially maybe even lists possibly. You may have talked a little bit about, say if you have a data structure and it's underlying one that you're using for the implementation is an array. Were you given any advice what to do when the array becomes full? Anybody at all? There is a practice that you might do if you need to make more space. Are there any suggestions of what you might do? So we talked briefly about the idea that you're going to resize the array by creating a new array, copying over your elements, and then you'll just simply just make that the new array, right? But the thing is, so think of this. Lovely, lovely, I love that. I love it. So think of it, there's actually a really interesting practice, and I'm going to justify that in today's lecture. It is called geometric growth. So I'm going to tell you about that. So if you've never heard of this, either way, I'm going to show you something that is both theoretically interesting and practically relevant. So if you might ask yourself, Dan, why do we care about some of these analysis techniques and stuff? I'm going to show you exactly why somebody might advise something for you in practice that actually is reflected nicely in theory. So are we all ready to go? Okay, so let's do this. Let's go over here. Let's go over here. So I'm going to say, as I'm being silly, we will show that the practice of doubling the size of an array or some other constant factor. So for example, if it's like 1.5 times the length of the array, or 3 times the length of the array, or 4 times the length of the array, or some other constant multiple is effective. So I'm going to show you, I'm going to motivate why you might use this practice if you need to resize an array for your underlying data structure, why you might use the idea of doubling the length of the array, or say if you want to make it, say, 1.5 times the length of the array if you need to resize your array. So I'm going to try to motivate why we might do this. So just to be clear, I'm going to lay out a scenario for us, and this is something that's very realistic for what we're looking at. So we're going to consider the example of what I'm going to refer to as an unsorted array dictionary. So you may have heard of dictionaries before. If not, you may have heard of them as maps. But if you haven't heard about dictionaries before, you can easily replace a lot of what I'm going to say with other data structures that are based on arrays, for example, a list. So what I'm going to do, so remember last day I talked about how I had a sorted array-based dictionary, where what I did was I have to put the elements, whenever I do an insertion, I have to put it into the appropriate spot, then I perform some shuffling to make room for it, if I have the space, right? Otherwise I have to resize the array. And we've seen there that the amortized complexity actually remains linear, which it's not very, that means that that very often you may have it where you're going to end up doing the expensive operations. That's the intuition behind it. I'm going to show you that if you have an unsorted array as your underlying data structure for, say, for example, a stack or a queue, or in our case, a dictionary, that you actually end up with some really, really nice results. And they're going to reflect something that you may have been told that is practically effective. So what we're going to do is we're going to start with an array. Start with an array of length 1, which is going to be 2 to the power of 0. So the thing that you need to be aware of is that we're going to be measuring this based on insertion operations, or so-called put operations. So that's what you need to be aware of, is that we're going to end up with a sequence of insertions that are going to happen. So in our case, the array resizing scheme is going to be that the array will be doubled whenever an insertion is attempted when the array is full. So you might ask, okay, so what should that look like? So remember, we're going to have, just to be clear, what we're going to be measuring are a sequence of put insertions. So we're going to be measuring, so the operation that we're going to be interested in is we're going to be looking at the so-called put or insert operation. So our scenario is going to consist of inserting n elements into or records into our dictionary. That's what we're going to be looking at. So just to give us an idea of what we're going to be doing here, is it okay if I move back over to this board? I want to get ourselves a little bit more space to play around with this. So we're going to be doing some put and insertion operations. We're going to do n of them. I don't know what n is. This is just a sequence. It's a general sequence. And the goal here is to have it and measure the cost of each one of these insertions for a general term. So I'm going to try to find how expensive each operation will be in my scenario. So I'm going to start off first with an array of length 1, and I'm going to perform a bunch of insertions into this data structure. And sometimes it's going to be where the array becomes full. Sometimes it's going to be where the array has room for a record to go in. So the things I want you to be aware of are from the last day. For example, we talked about some of these scenarios that can happen. So what does an insertion look like? Like if I were to perform a put operation into the dictionary, what would it look like? Well, it's going to consist of a potentially, it could consist of, so it might actually, where you actually perform the insertion, which you'll know where it's supposed to go because it's an unordered array, right? So I just keep track of this with a counter. So I know exactly where to place it in the array. Now, if the array becomes full, there's a possibility I'm going to have to copy elements. Likewise, there's also the possibility I'm going to have to allocate more space, right? I'm going to convince you through this, well, in this particular analysis, I'm going to only count these types of operations: insertions and copies. One thing I'll tell you is that on the assignment, I'm going to get you to convince yourself that if you were to allocate the memory, so if you count how much memory you require, it doesn't change the overall result at all. So you can get away with being a little bit careful about just doing insertions and copies, or you can add more things you want to measure when it comes to cost. Here we're going to measure the cost of insertions and copies. So let me give you an idea of what I mean by this. So I'm going to draw us a picture. It's going to help us really get an idea of what we're doing here. So keep in mind, I'm just drawing it bigger just to make it a little easier for us to see what's happening. So when I start up this process, so when I start my scenario, remember my scenario, I start off with an array of length 1. So right now, it will only consist of a single element over here. If I perform an insertion, the first insertion, do I have to do any copying at all? Or can I just insert the element directly in? I could just insert that, right? Now, to make it a little easier for us to figure out what's happening, anytime I just need to do an insertion, I'm just going to color that square blue. And whenever I run into that nasty case where we're going to have to resize the array, which means I'm going to have to perform copies and insertions, or sorry, copies and an insertion, I'll color those red. So when I perform the next operation, because remember, that's operation number 1, and I'm going to think about this like a pattern. So that's operation 1. I just do the insertion. Operation 2. Should I color this square? Keep in mind, this doesn't quite exist yet. Do I color this square blue or red? It's going to go red. So just a reminder, when we start this up, our array only consists of one spot, right? So what happens is when the array becomes full, we double the length of the array. Then I perform some copies, right? And then I do my insertion. So I do the insertion just like that. How about the next operation? Is it going to be our inexpensive case or the expensive case? Yeah, it's going to be red again. Very good. So in this case, notice that my array is full. So I'm going to double the length of the array. And then I can perform a copy over all the elements, and then I perform my insertion. Okay, how about the next one? Operation number 4. This one's blue, right? I have room to just insert directly. Okay, how about the next one? Red, right? So now notice that now I have 4 elements, so I'm going to have 8 elements, right? I'm going to double the length of the array. So the array's length gets doubled. And then I perform all those copies, and then I do my insertion, right? So now, what should go here for the next operation? Is it just an insertion? Yeah, it's just an insertion, right? Because now I have room. How about this one? Is this one blue or red? That's blue, right? So notice that now I'm getting more and more inexpensive operations. How about this one? Blue, right? Very good. Okay, how about this one? Yeah, that's red. Very good, very good. So notice that in this case, you would double the length of the array, so that its length is 16 in that case. But believe it or not, you'll notice that what we did just now is we talked actually about what looks like two scenarios. There's two cases that always happen here, right? When I measure insertions and copies, there's exactly two cases. There's the cases where I have the blue squares and the ones with the red squares. And what I want to do is I want to determine for a given operation I, how expensive that operation is. So I want you to think about this. And I must stress that in the notes, I'm going to include a table if you find yourself not entirely convinced by what we just did here. So I'm going to walk us through thinking about this. So I'm going to say, we will define the time taken or cost. So I'm going to call this C. So C is going to be the cost. So it's a cost function, where I is going to be the operation. Cost C of I of an operation I. So we're going to define this. And it's going to be based on these two squares, two types of squares. So I'm going to try to create a function that's going to represent the cost of performing each operation I. So for example, if I put C of 1, that's the cost of operation 1. C of 2 is the cost of operation 2 in the sequence. C of 3 is the third operation's cost, and so on. So the whole idea here is that if I can figure out how expensive each operation is in my scenario, does anybody have any ideas what I could do with those costs to figure out the total cost? What could we do with those? Yeah, well, now that if I know how to do this for each one of the operations, all I have to do is sum over all of the sequence operations. Notice that all I have to do is take C of 1 plus C of 2 plus C of 3 plus C of 4 plus C of 5 all the way up to C of n. And that's all I have to do to figure out the total cost of my sequence. So I told you that it seems like there's two cases, the blue squares and the red squares. So I'm going to give these names to just make this a little easier for us to talk about. So the red squares, sorry, that's a little bit of a fun noise. I'm making sound effects here on this as we're doing this. So I have the red squares and the blue squares. To make this easier for us to chat about, other than the blue and red, if ever I need to talk about the red squares or the blue squares, the red squares are going to be what I'm going to refer to as case 1, and the blue squares are going to be case 2. So if ever I use the word red, I mean case 1. Whenever I use blue, I mean case 2. So you're going to see it's going to break into two cases. And now I want you to notice something that's rather interesting. Let's start off first with the blue squares, case 2. So we're going to start off with case 2 first. So if I'm suppose that the cost of performing a copy is 1, and the cost of performing an insertion is 1, which if you think about these numbers, they could be, I've just chosen these, but they make very much sense if you think about it in terms of the time taken. Because if you think about it, because we have an unsorted array, to perform the insertion, I know exactly where it's supposed to go in the array, right? It should take constant time if I perform the insertion when the array has a spot in it for me, right? And to perform a copy, Well, this is going to correspond to me going through the loop, copying over each of the elements from one spot to the other. Each one of those is a cost of 1. If I do it across all the array, you should expect something that's linear, right? So that's where these numbers come from. I just chose these. If, for example, you're doing this type of analysis and you've wanted to really place emphasis on, say, the copies, like you don't want copies to happen, you can make these as expensive as you like. But I'm just trying to make them match up with our time complexity analysis that we've done, which I argue would make a lot of sense, right? So are we okay with this so far, that I've assigned the cost of inserts and copies to be 1 each? So they shouldn't appear like magic numbers. They're just me using the time complexity idea that we've been talking about all previous to this. That's where they come from. So let's talk about the two cases here. So suppose that I give you a case, one of these operations is the blue square. How expensive is the blue square? How expensive is the blue square? It's just 1, right? All I do is do an insert. So this is just, I'll just say otherwise here because I have to give you the other case. This is the easy case. So this is just case 2. And this is when we have an insertion. Sorry, that N looks like it just sort of morphed. Let me fix that. And it turned the O into an A. This, of course, takes constant time. Hence why we just say the insertion just costs 1. This other case, so this is where we have the red squares. Now, the intuition behind this is as the array gets longer and longer, this red square business, all these cases with the red squares, these darn red squares, whenever those happen, they're going to happen less and less frequently. Does everybody see that? So notice that when I doubled it and got to length 8, notice there's more blue squares. You're going to see that as the array's length gets longer and longer, you're going to see more and more blue squares. But it isn't just that it just gets bigger. There's actually a quantity to how much more frequently the red squares can happen, or infrequently they can happen. So when I perform the red square for operation I, let's think about it. What is happening? So suppose I'm right here at this one. This is operation number 3. What happens here? Well, I allocate the space for the new array, right? I'm not measuring that, right? I'm measuring only the copies and the insertion. So how many copies are happening? 1, 2. So there's 2 copies happening. And then I do the insertion into this spot, right? So in that case, how many operations are happening if I'm measuring them based on these costs here? And for operation number 3. Yeah, 2 plus 1, perfect. So just like if you were to go over here and say when I make the array of length 16, notice that I have to copy all of these elements. How many are there? There's 8 of them, plus my insertion. Yeah, very good, very good, very good. So if I'm looking at operation I, notice the place where I currently am. I'm just sitting 1 outside of the original length of the array, right? So if I look at operation I, the cost of doing that is I. And when does this happen? When does it happen? It happens when the array becomes full, right? But when does that happen if you think about it? It happens when I need to double the length of the array, right? But here's an interesting thing to think about. When does that happen? It surely isn't like some linear number, right? Every time I double the length of the array, it isn't just simply, oh, it's 2 times the original length. Like, sure, it doubles the length of the array, but it's actually just exactly, and the chat has got exactly right. It's actually exponential. So every time I double the length of the array, if I look at it with respect to my operations, every time I'm doing this, I'm doubling the length, but every time I'm doubling like the entire length, right? So when I do this, this happens if in the previous operation, I'm at a power of 2. So if I minus 1 is equal to 2 to the power of k for some k greater or equal to 0. So this is case 1. You might ask what exactly the I comes from. Sorry, I was just getting really excited here. This happens because there's I minus 1 copies. And then there's just one insert that occurs. So I'm hoping that everybody stuck around for this. So remember, what was the length of the array before I performed this? Well, in the previous case, it had to have been some power of 2 because every time I double the length of the array, right? And it starts at 2 to the power of 0, so if I double the length of the array, it has to become 2 to the power of 1 when I resize it. Then when I resize that array, it's going to become 2 to the power of 2. Then when it resizes the array again, it's 2 to the power of 3, and so on, and so on, and so on. But notice that I actually have some relationship between I and this 2 to the power of something. So notice that our doubling is actually just sitting right here. So for example, if I was tripling the length of the array, instead of this being a 2, it would be a 3, for example. If I was quadrupling the array, it might be, instead of a 3, it might be a 4. But notice that the idea here is that the expensive operations, as k gets larger, happens more and more infrequently. Does everybody see that? Are there any questions of where this came from? Just to be clear, because we're going to use this. But yeah, I have a table in the notes that you can see after class that shows you how you can try to detect this pattern if you find yourself just really not convinced by this. So if you don't like the blue square, red square, and you prefer to just look at a table, I have a table in the notes. So anyways, we got to come up with how we're going to determine the total cost. Now, remember, like I said, if I want to figure out that total cost, well, that's simply going to be the sum over all my costs, right? Where I start at operation 1 and I go up to operation n. So if I could figure this out, and then I could just divide that by n, we're done, right? That's all I have to do. One question I do have for you. Assuming that I pick appropriate costs for my operations, in this case I did, if I sum up this, what would this represent? What does that represent again? The total cost in terms of time complexity. What would this be? What does that be? Sorry, I'm getting really excited here. What would that be if I'm talking about time complexity, just generally, before I divide it by n? Think back to how I defined amortized analysis for you. So remember, it's worst case per operation, right? So what would it be if I don't divide by n? So if I don't divide this by n, what is this? Any ideas? Well, I'm not talking for a specific asymptotic. I'm not looking for the result here. I'm more wanting to know what this represents. So what does this represent from a time complexity standpoint? So if I don't divide this by n, and remember, amortized complexity means worst case per operation. So if you think back to your measurements, so instead of it being worst case per operation, it's just worst case, right? But it's not just worst case of a single operation, it's worst case over all of those operations, right? So this is actually where amortized analysis can become very useful. For example, when you calculate all these costs out, and suppose somebody gives you the amortized complexity. If you know how many operations are going to happen, and you multiply by what is the amortized complexity, you can figure out the overall worst case time complexity of building your entire data structure. So if it takes n operations to build your data structure, then it's simply no different than summing all these costs, which that will be the worst case scenario if you're measuring it by n operations, but as opposed to just a single operation. So this is often useful for when you're analyzing data structures, because sometimes you have it where you have an algorithm that builds a data structure. Say, suppose it performs n insertions. It builds and maintains some data structure that you use. If you know how this occurs, from an amortized complexity standpoint, all you have to do is multiply it by how many times you apply that operation, because it's worst case per operation. And if you know that, then surely if you know how many times you're doing it, you could just multiply that by your amortized complexity. And you'd get this. But yeah, I thought I would just bring that up as more of a conceptual thing to bring up, because it will every once in a while rear its head up, and you might ask, why does amortized complexity tell us this? And I'm trying to explain that right now. So anyways, let's head over here. And we got to talk about how we're going to use this cost function to get the amortized complexity, okay? So we have two cases, but I need some way of breaking those cases up by when they occur in relation to like what I'm measuring, right? Because remember, I'm summing over all those costs, right? Sometimes C of I is going to be case 1. Sometimes C of I is going to be case 2. I would like to be able to break those into two pieces so I can measure them separately. So I'm going to end up with two things I'm counting, case 1 operations and case 2 operations. So I'm just going to, for the sake of time, I'll let you think about this. Case 1 occurs because every time it happens in relation to a power of 2. It occurs the ceiling of log base 2 of n times. Just if you find yourself curious about why, remember, every time case 1 occurs, it happens just after it sits at a power of 2. So surely if I take a power of 2 and I just round it up, I'll know how many times it has to happen. So occurs the ceiling of log base 2 of n times as the array is resized whenever I minus 1 is equal to 2 to the power of 0, 2 to the power of 1, 2 squared, all the way up to 2 to the power of the ceiling of log base 2 of n minus 1. Now you might ask, where did that come from? What I advise you do is try what we just did with the blue square, red square exercise. Try it with a fixed length. So for example, make like n8 or something and convince yourself that that exponent is indeed correct. So just remember, I start off at the exponent 0 and I go up to 1 less than that. That's where this count is coming from. Why? Because every time I do one of these case 1 situations, it's always because it's 1 higher than a power of 2, not at a power of 2. So there's case 1, this is when it occurs. Now case 2, case 2 happens every, now remember, we know how many times case 1 happens. So how many times does case 2 happen? It just happens every other time, right? So if I have n operations, it most certainly happens all other times. Which is n minus the ceiling of log base 2 of n, right? Right? It's n minus how many times the other case happens. So with this information, what I could do is I can actually figure out the total time taken. And then with that information, I could get the amortized complexity. Then the total time taken to perform a sequence n of put operations, put or insert. I'll call it put because we were already using the word insert. put operations. Like I said, if you're talking about a different array-based data structure, like a array-based stack, you could say push instead of a put. Put operations is, now this is my t, so this is my function t that I defined at the beginning of lecture. So t of n is going to just simply be the sum of all the costs, right? Just like I said a moment ago. Then I'm going to split it into these two cases because it's easier for me to count them when they're separate. If you had a very simple way of counting all of how many times these happen, you don't have to do something like this. If you know, for example, every operation takes one cost, like every one is just a cost of one, then you don't need to pull out something this sophisticated. You can just simply just count them and sum them together, right? Here it's a little bit more complicated. So in case 2, the cost of that is 1. And how many times does it happen? N minus the floor of log base 2 of n. So this is case 2. That's case 2. Plus, now, I'm going to do a little bit of a trick with you, just because I want it to stay so that I can count over all these exponents. And I have a relationship between I and k. So you're going to see me do one small little detail here I just want you to pay attention to. So I'm going to count this from k is 0 because remember the exponent starts at 0, goes 0, 1, 2, all the way up to this. So I'm going to start at 0, go up to the ceiling of log base 2 of n minus 1. So my lower limit is 0. The ceiling is the ceiling of log base 2 of n minus 1 of 2 to the power k plus 1. You might ask where this plus 1 business came from. Like, where did this come from? Remember back to our cost function. Remember, we know that it's I minus 1 is equal to 2 to the power of k. So if I want this in terms of I, remember operation I just simply add 1 to both sides of this equation, and I end up with I is equal to 2 to the power of k plus 1. That's where this comes from. So remember, all this is just me writing it in terms of operation I for case 1. So this right here is case 1. So this is all the cost of case 1. So it's a little bit tricky. I could most certainly say, yeah, that's a little tricky. Just remember, what's sitting right here is actually just the cost of performing operation I when case 1 occurs, which in terms of I is just simply 2 to the power k plus 1. So I'm just summing over all of those because I know how many times they're happening and I know how expensive each one is. And at that time, remember the cost of operation I is I, right? But notice that I want to be able to talk about what that is in case 1. So does this help everybody see where case 2 and case 1 come from in the way I split up the costs here? So notice that what is actually sitting right here is actually I. If you don't see that, just look at my equation I wrote over here where I just rearranged for looking for I and I substituted that in. So that's what I is when I sum over all of them as I did up here. Okay? So what you could do further is you could simplify down these expressions. Now, for the sake of our time here, I'm going to simplify it a little further down because we lost a little bit of time there. So I will have the full analysis in the notes if you want to go through carefully through all the steps here. So I'm going to work us down a little further. So notice that I have some terms here. I have some that are involving n minus something. Then I may split this apart a little bit. Because notice that this has 2 terms in it. I might split this sum into 2 sums. If you end up with 2 sums, what you could do is you could use a closed form on the rightmost one with a term of 1. And you'll end up actually with a count just like that looks very similar to this. So what will happen is you'll end up going a little further along. And you'll end up with something that's like n plus the sum of all those exponents there over each k. And if you simplify this down a little further, you'll end up with effectively a geometric series, and you could apply a geometric series closed form because it's a finite number. You can, even if it was infinite, you could still do this. But effectively, what happens is after you apply that closed form, you're going to end up seeing that this is going to be strict. This is all strictly less than n plus 2 times 2 to the power of log base 2 of n. Like, there's a lot of steps that I skipped here. So just please take a look at those in the notes. And then what happens is, you see, it's 2 times 2 to the power of log base 2 of n. And I have a question for you. What's 2 to the power of log base 2 of n? Because somebody remembering their definitions of logarithms could tell me. What is 2 to the power of log base 2 of n? What is that? It's just n. Yeah, it's just n. So all I have here is I'm going to end up with n plus 2n, which is going to be equal to, of course, 3n. So if you actually were to sum up over all these operations, believe it or not, it's only going to be a linear number. It's 3 times n, believe it or not, which is actually quite nice. It sort of matches your intuition anyways, because if you had a whole bunch of these operations occurring, remember, I'm looking at the total cost of all of them. I haven't computed the amortized complexity yet. So you should expect something that looks linear if I perform some n number of operations, right? You should expect something that looks kind of linear. So let's go back over here. And let's wrap this up, because we still got the amortized complexity to calculate. But yeah, I highly advise going to the notes and looking at how I got to that step. There's several steps I skipped there. But I laid them out in quite detail, so if you find yourself just really like, where did that come from? It's all broken down quite carefully for you. And it's not too terribly complicated either, which is great. Therefore, the cost of put, so this is our put operation I'm referring to. Well, what's the cost of this? Is T of n over n, which this is at most 3 times n over n, which is equal to 3. Amortized. Which is big O of 1, or big theta of 1, amortized. So the amortized complexity of performing n insert or put operations into an unsorted array dictionary is constant, amortized, which is wonderful. So the amortized complexity, just to reiterate, is constant. So what does this tell you? This tells you that many of these operations, they don't actually contribute much to those worst case scenarios that we were dealing with previously, where the resizes happen. It ends up that all of those really inexpensive operations, the really cheap ones, they happen so often that you won't really have to worry so much about that worst case where we have to resize the whole array. So like I said earlier, you're going to find that many of the operations, these cheap ones, are going to effectively pay off the expensive ones. But yeah, so this should match the intuition that you may have had previously, that, oh yeah, no, if I resize the array, but I always do it by some constant factor, so big O of, it's 1. It's 1. Big O of 1. Yeah, it's constant. Yeah, so I would tell you that that performing a sequence of n put operations has big O of 1 time amortized. But yeah, so this gives you a much more delicate way of looking at a sequence of operations. So you could you decide the operations, you assign costs to those operations, and then you figure out a general form for a given operation I, and you sum over all of them. and then you just simply figure out what that is, divide it by the number of operations, and that's it. That's it. That's the aggregate method. So just to kind of recap what I said here. So doubling an array's length is an example of geometric growth. So if ever you talk to somebody and like, okay, so what's this practice called of doubling the size of the array or tripling the length, or it's often referred to as geometric growth of the array. Is a good choice. And this amortized analysis reflects the practice of doing this. So this analysis helps you get a practical insight as well as it reflects back on the theory that I've been talking about before. So I'm hoping you found that this amortized analysis helps us when we talk about data structures in a little bit more of a careful way than we did before. But you might ask, okay, so why should I care about this geometric growth? So different programming languages will have their own standard libraries, for example. And you may have heard of things like vectors, for example. You may have heard of vectors before. They are an example of a dynamically resizable array, right? That's effectively what they are. They're a dynamic array or resizable array. You could also think in other languages, for example, in Java. This is one that I like to pull out. You may have heard, if you ever used Java before, you may have heard of the ArrayList class. And if you're wondering what this number, like I talked about the array doubling, this term that they use is called the growth factor. So in this case, when I double the length of the array, its growth factor is 2. Java's ArrayList class uses a growth factor of 1.5. So if you ever wonder, Dan, when you show me these things, how do they reflect in things that you actually try to use in some languages? They come every once in a while. And this one, I love to show this example so it reflects both on both sides. So you aren't just seeing, oh yeah, there's this abstract kind of analysis. Believe it or not, this is very helpful when we look at data structures. And in fact, these are things that are used in practice. So in this case, like if I talk about the ArrayList class in Java, they actually do use this principle. But yeah, are there any questions about this? Any questions at all? So doubling the length of an array or making it 1.5 times bigger, this is a rather good way of resizing an array, at least theoretically speaking. Now, you might ask, Dan, what if I just, instead of it, for example, so you always double the length of the array or triple it or make it 1.5 times longer. What if instead I add a constant? Like say, for example, every time I resize the length of the array by like 50 or something, or 100. So if the array was, say, length 100, I add, say, 100. And then I add another 100. And then another 100. So I added by some constant factor instead, sorry, constant additive term as opposed to a multiplicative factor. You might ask, does that make a difference? And believe it or not, the amortized analysis will actually spell this out for you. So I've actually included this actually as an example of how you could take this analysis and easily tweak it to talk about other cases. So for example, if you were to, so I'm just going to say amortized analysis can also inform us for other array resizing schemes. And I'll include an analysis for you in the notes. For example, increasing increasing the length of an array by a constant. So in this case, if you pull out the amortized analysis, you'll find that it actually is a very poor practice. It actually does not actually get you the same type. Like, notice here that the amortized cost is going to end up being constant. It's only like 3. That's really nice. So you might ask, okay, so what happens in these cases? Well, believe it or not, in this case, you actually get the same kind of result that we got actually last day. So you could actually show using amortized analysis that this actually is going to end up being big O of n amortized, as opposed to constant. So if ever somebody's asking, okay, so which one of these two schemes might be more ideal? You might want to go with the one involving geometric growth as opposed to using a constant factor, like a constant term to extend it by every time. Otherwise, you might have to bite the bullet very often if you require your array to be rather big. So the easiest way, obviously, to get around this whole issue of resizing the array is, of course, just making your array big enough that it fits everything you need, right? But I just wanted to make sure that you're aware that, yeah, no, if you ever need to resize your array, there is actually a concrete way you could analyze them just like this. So are there any questions about this at all? I wanted to really show you this because I think it's a lovely example of how amortized analysis gives us a very careful way of thinking about something that you actually probably run into at some point. But yeah, in practical terms, I'd recommend using geometric growth resizing schemes as opposed to just adding them by some constant amount. Like, basically just don't add like 5 to the length of the array or add 100 unless you know that your array most certainly won't be needed to go that much longer. But yeah. So if there aren't any questions, I'm going to head over here. I'm going to have a couple of quick remarks about amortized analysis. And depending on how much time we have here, we might start our next topic a little bit. So I just have a couple more remarks I want to make about amortized analysis before we proceed. So this isn't going to be the last time we're going to see amortized analysis. Just I'm going to presume that you have an understanding of what amortized analysis is. Because I'll usually just bring it up more as a fact. And if we have time, I might derive it for you. But most of the time, worst case analysis is what I'm going to kind of stick at, unless it's actually incredibly relevant. That's why it's often handy, is that I have something a little bit more fine-grained. I can go in with my data structure and kind of like scoop it like a scoop of ice cream right out of the bucket. I can get my hands dirty with that. So what exactly can we do with amortized analysis? Remember, it's about data structures and we have a sequence of operations occurring. So this isn't actually the only method that exists for amortized analysis. I want to bring up some couple other well-known techniques. There are 2 other well-known amortized analysis techniques. Now, for some of you, depending on what kind of background you have, you might find some of these techniques rather helpful or insightful to get a grip over this concept. If you don't really like the aggregate method, there do exist these other techniques. And some of them actually are the ones that you have to pick up to understand some more advanced data structures. We'll see an example of one such data structure a little bit later on. When we start talking about splay trees, I'm going to bring up some things about amortized complexity there, but I'm not going to be going as deep as I did here just for the sake of time. But I just want you to just be aware that there's these other techniques. So one example is the so-called accounting or banker's method. So this is, of course, inspired by finance. Inspired by finance or accounting. In this technique, you assign prices. to the inexpensive operations that you earn. So the idea is that it's inspired by accounting and finance, where you assign prices to these inexpensive ones, and you earn these. And you got to think of it almost like I'm charging a little extra. So if I have a really cheap operation, I want to be able to get a little extra off of performing each one of these, so that I could use them to pay for the expensive ones. Just like if I think about this in terms of like a loan, for example, you may have a lot of smaller priced, like you might find like an appropriate interest rate, for example, and you're charging, you're paying off it in little pieces. And the idea is that if, say, for example, he comes along and you want to pay off a large chunk of a loan, if you can, you want to make it so that it's at an appropriate rate so that when you pay it off, it isn't going to hurt you when it comes at the end of the day when you want to pay off the whole thing. So the pay it off, I'll say pay, instead of pay off, I'll say pay for expensive operations. Expensive operations. I like to think of it like taking out a loan. Another one is the so-called potential method. So the potential method, this is inspired by physics. You can think of the potential in a system. So in the potential method, the idea is that you derive something called a potential function that's going to measure the so-called potential of the system itself, which is your data structure. So in this case, it would be your data structure. And what you do is you measure the potential of your data structure when certain operations are occurring. And then what happens is every time you change the data structure, it changes the potential of the system. And you want to do is you want to measure how much the data structure changes from one state of potential to another. So you look at what happens at the end versus the beginning, and whatever happens in between your operations. And these are natural and analogs for calculating out the total amortized complexities, that you figure out what's the potential that happens between an operation before and after versus the overall system before and after. But I'm not going to talk so much about that, but it's about observing differences in this so-called potential function that gets derived. Out of these types of analyses, I would argue that the potential method is the most complex one. Some more advanced data structures use sometimes these, and some algorithms even will pull out this potential method sometimes. So it isn't necessarily tethered only to amortized analysis, but it is most certainly the idea of a potential function. Sometimes gets used in algorithm analysis for determining the running times. In this case, it's determining the cost of an operation versus all of them. But yeah. So that's amortized analysis. Rather than starting the new topic, what I want to ask for you, there's two things I want you to do before we get to next class, or at least, actually one of them you don't have to do before next class, but most certainly you'll need it for the assignment, is that I'm going to ask you to read there's a section on trees that I have. So there's a section, it's because of the way the course has been scheduled this term, is that I want to make sure you have some review of general rooted trees and just how you can you could perform operations on just a rooted tree as opposed to just a binary tree. So just give that a read. I did actually post a link also to a lecture of me talking about it as well. So if you don't want to read the notes, you can always just watch the lecture. But the other thing is I want you to just, I'll include it in the notes, is I want you to just take a look at the priority queue ADT. We're going to talk about next class, we're going to talk about priority queues. I'll include in the notes the priority queue ADT. And I want you just to read that, and we'll come back next time and talk about priority queues. Okay, everybody? So I say thank you very much, and have yourself a beautiful day. I'll see you later.